Okay, so to the latest video, but this is the discussion video for this week. As usual, we start off with a couple of easier problems and then a few themed problems. So let's get right to it. The first problem. Um, so if you read it, basically you have a bunch of numbers. So first line is the number of cases, and in each case, you have number of guests, followed by a bunch of numbers. There at most 50 cases, and the number of guests is at most 1,000, and then the guest IDs are it's between 1 and to the 31 minus 1, so basically a normal 32-bit integers. And you're supposed to figure out how many people, how many numbers are not paired up. Okay, so for example, here, you have three numbers here, but the large number is paired up, so the only one that's not paired up is 1. In the next case, um, there's actually exactly one guess, exactly one number that is not paired up. Okay, so you have to figure out the number that's not paired up. So basically, there are many ways you can do this, and you just have to figure out how to keep track of how many I guess who are paired up or not. You can, for example, you can take the list sorted. If you sort it, then all the things that are paired up are together, and then you can scan it that way. You can use a set to see who has shown up, and then if you see a number the second time, you know that it's not the one that you want. And you can remove it, I guess, from the set. So the approach that I chose was to use a map. Um, Again, there are many, many different ways you can do this, but I basically use a map where the first item is the value, the ID of the guest, and the second argument is how many times I see it. So I run through a standard um, loop that read through the G numbers, and for each one, I increment the appropriate spot, and then I just go through the list, go through the map, and say if the count is 1, then I print it up. Again, there are many different ways you can do this. Perhaps if you don't want to use any data structure, just read into an array and sort it, and then things have to come in pairs, except the one that's singled out. Okay, there's not too much more for me to say on this problem, so I'll move on. Another brick in the wall. So if you read the problem, basically you have the height of the wall, the width of the wall, and then n is the number of bricks, and then n numbers, xi's are the length of each brick. And these bricks have a height of 1. And you want to know if you can actually build a wall of size height h, and you must lay them out in the sequence that they give you. So you lay it on the bottom, and then when you fill up the bottom level, you go to the next level, and so on. Okay, so that's the idea. So if you have a wall, right, h and length, whatever they call it, L, then basically what you have to do is you have to put the first one here, then the next one here, and you keep going until there's some point that's called K, where the sum of the first K plus 1 bricks is exactly equals to the length of the wall. When that happens, then you start the next one, which might be shorter or longer, and so on. And you repeat the process. Eventually, hopefully, you will fill everything at the top. Okay? So what can go wrong? What can go wrong is that you run out of bricks, for example, and then you don't fill that high. Or when you get to this spot, let's say you get to this spot, You fill out all this part, and then the next one will go out of bounds. And in that case, you're not allowed to skip that brick. You're not allowed to put another brick in its place. You must use the next brick. So in that case, you say no. So basically, all you have to do is keep a running total of the length of the current layer. And if it ever equals exactly length L, you move up to the next level. If it ever goes over, then you say no. And just keep doing that until you run out of bricks or you get to exactly height H. And so this is a little bit of a bookkeeping exercise, I guess. So just quickly show you what my code looks like. So I read in the height, sorry, it's not L, it's W, height and width, and then N. Then I have a vector of bricks, and I used this trick before in previous videos where I have a vector of N integers, and then I use this for auto ampersand X, so that will loop through all the items in the vector as reference, and then read into it. And then I'm just going to have what I call current height and current W. So current height is the current height of the wall that I have managed to build completely. And current W is the width of the current layer, the bottom layer that I'm building. And at the beginning, I just assume that everything is good. Okay, so I go through each of the bricks from I equal to 0, I less than n, I plus plus. But I also only keep going if the current height that I manage to build is less than h, because I don't have to use all the bricks. If I manage to get all the height that I want, then I'm good. And I'm not going to increment the current height unless the layer is exactly full. So when current height equals to the height that I'm looking for, that means that all the levels are exactly the same width. Okay, so first thing I'm going to check is if putting the next brick, is it going to blow? Is it going to be over the width of the wall? Okay, so current width plus the next brick, is it bigger than the width? Then I know that it's bad. Okay, so I just say good equals false, and I break out the while loop, the for loop. There's no point going on. Otherwise, I put the brick on the current level, and if I reach exactly the correct width, then I reset the width to 0 and I increment the height. And that's all I'm doing with this keeping track. And then at the end of here, if I get out the for loop, I can get out in 3 different ways. Maybe I got out because good is false. Maybe I use off all the bricks, or maybe I reach the height. So the only good situation that I want is to make sure that the height is reached. So I compare height and current height. If it's true, then I want that to be good, unless I already set it to false. So this is a little trick, I guess. If current height is equals to h, then it's true. Then good n equals, that just means good n, the old value of good, and the new value. So if it was already true, then then it will be set to this value. If it was already false, then no matter what this is, it's always going to be false. Also, because this is the only time I update the current height, the first time that this breaks out, it's guaranteed that the next layer has not been done. Not that we really care, actually, but just a little observation. As long as we can fill exactly H layers correctly, then we really don't care what happens with the leftover bricks. Okay, so I guess this is this one. There's not much more to say. Maybe there are other ways to keep track of this, but this is probably the easiest way that I can think of anyway. Okay, so now let's get to something that's a little bit more interesting. All right, so the theme of this week was supposed to be graph algorithms, And I'm starting with some pretty standard graph algorithms here. So again, I'm assuming that you read the problems. Basically, you're given a grid of black and white. You want to know how many loops there are in how many loops there are. They're made up of black squares. And the black squares, you're told that these loops will never touch each other. Okay, so this loop here is completely separated from the other loop, and so on. And you're also told that the loops always start from one place and loop all the way to the end, although that's not exactly too important. But you can have loops within loops. So here you have a big loop on the outside, and then you have 3 loops on the inside. You're still supposed to produce 4. So basically, if you have learned anything about graphs, this is basically what we call connect component count, counting connected components, right? So if you say that 2 black nodes are connected if they're next to each other, whether it's vertical, horizontal, or diagonal, then all of these ones in the outer loop and then any other loop, they're connected to each other. Okay. And so what we do is we do a connected component analysis. So how do we do that? There are many different ways we can do that. And one of the standard ones that you do, it's depth first search. So basically, what you do is you ignore all the white ones, and then you find the first black one here, whatever that R and C is. And what you do is you say, you have a function, let's write it recursively, and we will start searching at the location R and C. So this is undo. It's vector. Actually, let's not do this. Let's have what do we want to call this grid? Let's call it the character array A with the appropriate dimensions. So character A, what's the appropriate dimension? I forgot. Up to 100. So we'll do 100, 100. And it's either, okay, what would it, it's pound or dot. So pound is black and dots is white. Okay. So what we're gonna do is we're gonna look into all of these things. There might be many of them that are connected, and we are going to erase it. So why am I erasing it? Erasing it means that if I erase all of them, turn them all into white, then I just have to remember that I call this DFS once. Every time I call DFS on a black cell, I know that there's one loop, and the DFS will go and wipe it out so that I won't accidentally count it again later. Okay, so wiping it, prevents me from counting it multiple times. All right, so what do I do? So I'm assuming that I call it on a box that's black. Otherwise, this is not going to work. So the first thing I'm going to do is I'm going to make it white. Okay, I'm just going to get rid of it. Then the next thing I'm going to do is to look around me for each neighbor. So now, if I'm at here, this location, I have 8 neighbors because I have 4 horizontal, vertical, and 4 diagonal. And there are multiple ways you can do this. And the way that I like to do this is to have what I call a DR and DC array, delta change in row and change in column. that step through the 8 positions. Okay, so for example, here, this is R minus 1, C minus 1. So I would represent this as minus 1 and minus 1. This, it's R minus 1 and C, so I represent this as minus 1 and 0. And then minus 1 and 1, negative 1, so it's 0 and negative 1. This one is R and C minus 1, so this is 0 and negative 1 in terms of dr and dc. 0 and 1, and then 1, 1, 1, minus 1, 0, and 1. That would take care of these. And what I do is I just say for int some direction equals the 8 direction that I'm considering. Then I can say the neighbor R2 is just R plus dr d, and C2 is C plus D, C, D. And this will step through R2 and C2 in each of the 8 neighbors. Now, you don't have to do this way. I mean, you can hard code these 8 coordinates in R minus 1, C minus 1, R minus 1, C, etc., etc. But this is a lot easier to manage. Yes, you have to write this to dr and dc arrays, but the main logic of the loop is much clearer. Okay, so now I'm looking at the neighbors. What do I do? If the neighbor R2 and C2, it's also a black one, then what you're going to do is you're going to just follow along and recursively trace it with the DFS routine, and it will go and recursively erase the whole thing. Now, this is actually a little unsafe because when I just look at my 8 neighbors, if R and C is right here, some of my 8 neighbors are going to be out of bounds. So I actually need to add a bound check. Okay, so you can see in my code later how I do that. Alternatively, if you don't want to do the bound check, you actually don't have to do the bound check. You can create an array of 102 and 102. Why 102? Because I'm gonna put the real thing in the middle and have a 1 pixel boundary that are all white. So you're never gonna call DFS on the boundary. You only call the DFS inside here, and then because of the way we created this grid, we are actually never gonna go out of bounds. And so you never have to do bound checks. Okay, either way, doesn't really matter which way you handle this, but you need to be aware that you have to deal with this bound check potentially. Okay. And that's the DFS function. That's one way to do it. And what you do is you go through your grid. Whenever you see a black square, you call DFS on that square. That will wipe out all of the black squares belonging to that loop. And so that would be 1. You count that. And then you look again for another black pixels. And then you call DFS again, and you keep doing that every time you find another black pixel. That's the start of another loop. And then we call DFS to wipe it out of the map. Okay, so I'll show you my implementation. Okay, so here it is. So I have grid M and N. I call it grid 100 by 100. I have the dr and dc array that we talked about. I have a function that checks if a certain coordinate is inside the boundary. So it has to be between 0 and n minus 1. For row, column has to be between 0 and n minus 1. And then DFS, this is basically what I said. If you set the R and C to be white, Then you go through the 8 directions. R2 and C2 are set to the coordinates of the neighbor. If it is inside and it is black, then you recursively call DFS. And then finally here, solve. I have how many components I've found so far. It's 0. I go through my loop. I go through my grid. If I see a black square, I increment the count because I found another one. I call DFS to basically wipe that off the map. So then the next time I find another pound sign, it will be a different loop. Okay, so that's one way to do it. But there's a second way of doing it, and I'm not saying, well, okay, there are other ways of doing it. There's a third way that I have not implemented, and if you know DFS, you might also have heard of breadth first search. It's a different way of searching for connected components, but it works. At least maybe we'll find a connected component to say in a slightly different way, but it will find a connected components. So you could have used BFS as well and do essentially the same thing. Okay. All right. So what's this third? What is this other thing that I implemented? Okay. So you have up to 100 nodes, boxes. So I'm just going to number them. So this is N and this is M. So up to N minus 1, and then N plus 1, and so on. Okay, and then all the way to N minus 1. And in general, if this is R and C, then this converts to the number is R times N plus C. Okay, so every box has an ID. Okay, unique ID. So what am I doing with this? What I'm going to do is I'm just going to scan. I'm going to pretend that at the beginning, all of these IDs are separate groups. Okay, so 0, 1, 2, 3, all of them are separate groups. Okay, and we're going to use a data structure that I probably have talked about, disjoint sets, also called union find, to keep track of sets that are joined together. So every time I see 2 black boxes next to each other in whichever direction, doesn't matter, I take the ID of this one, I take the ID of this one, and I tell union find, please merge them together. Okay, that's it. All of these. Now, union find will merge things. It will not just merge these two, but if there are other things that attach to this, it will merge all of them transitively. Okay, so this is what is called dynamic equivalence relations. If you have taken Math 2000, you probably know what an equivalence relation is. So you can use union find to merge things that are connected to each other, and everything that is the same group will have the same ID when you call it. So UF dot find ID1 will return some number. Whatever it returns will be exactly the same as UF dot find ID2 or any other IDs that are in the same group. So what we're going to do is we're going to process these pairs of black boxes side by side, merge them all, and then at the end just ask how many different labels I can find. Now, of course, I don't count the labels that are for groups that are not belonging to a black pixel. And what I can do is I can just basically when all of these are in the same group, one of these IDs will have exactly this property. When you find the ID, it's exactly the ID itself. Only one of them. So that will tell you how many, the number of times this happens, it's going to be the number of components you have. So union find, it's in my code library. So here there's a union find class. You initialize how many elements, how many things you're keeping track of. You can call find, you can call merge. And basically, it's a little bit of a lie, but you can say that if you do n operations, it will take approximately n operations. So if you do n operations, whether they're find or merge, but if you have a total of n operations, the complexity is basically big O of n. Anyway, that's not absolutely true what I said, but it's good enough. Okay, so what do I do? I have a union find data structure to keep track of n minus m times n boxes. I go through all of the grid. If it's not a black square, I skip it. Then I go to the 8 neighbors, the same code I have. If it's inside, if the neighbor's inside and it's also black, then I merge the two indices. And so the two indices is, I have a function that computes the indices based on row and column. And then at the end, I just have a count, right? So I go and count how many times I go through the grid. If it is a black square and the index that's returned by find is exactly the same as the index that I put in, then that's another component that I found. Okay, so if you haven't looked into this union find, I strongly suggest that you learn it because it's a very useful data structure that's also very easy to use. And it's also extremely efficient, right? So basically, again, if you have an n objects, you keep track of n objects, and you want to do a large number of operations, let's say capital M or whatever to use to denote the number of operations you do, then each of the operations take roughly constant time. So the total amount you do for total amount of work you do for M operations is basically big O of n. And there's not much that can be more efficient than that. Yeah, so again, if you really look this up, you will know that what I said about constant time per operation is not completely true, but for practical purposes, it's good enough of a lie. Okay, the next two problems is about shortest path, even though they don't look like it. So you have a graph up to 10,000 intersections, at least at vertices, and number of corridors is 15,000. That's the number of edges. And then each edge has a number f, which is a factor between 0 and 1. When you pass through it, your size shrink by that much. So if f is 0.75, after you pass through it, your size is now 0.75. And they multiply together. So if you have 0.75 in one edge, and then you go through another one that's 0.1, now you're 0.075. Okay, and you want to be as large as possible at the end. Okay, and you can assume that's always possible for to reach the exit. So, so you have some kind of a graph. So you have a start somewhere, and you have an exit somewhere, and there might be multiple ways. These edges can be used both ways. Okay, so there's an undirected graph. Let's say something like this. And then you have the numbers, 0.7, 0.6, I don't know, 0.3, 0.8, maybe this is 1.0, and this is 0.5, etc. Okay, 0.25, 0.8, and 0.5. If you decide, for example, to take this route from start to exit, then on the first edge, you get reduced by 0.6. Then you get reduced to 0.3, and then you get reduced to 0.5 for a total of point something 9. So this is 0.18, 0.18, 0.09, I think, if I haven't screwed up. Okay. And if you take, let's say, this path, then it's 0.7 times 1.8, so that's 0.56. So this path is better than the bottom path. But is that the best path? Well, in this case, it probably is, but in general, how do you find the best path? Okay. You want to be as big as possible. Now, you're looking for paths that try to maximize a certain number, and there's no standard algorithms that maximize the product. Okay, so usually when we talk about the cost of a path, we usually add up the cost. We don't multiply. But there's a trick. Whenever you want to multiply stuff, okay, so if you're trying to do, I don't know, A times B times C, you can turn it into sum by doing log. Because log of A plus B plus C is log of B plus log of C, like this. These two things are the same. So if you can optimize, instead of using the factor that they give you, put log of all the weights. Now you're trying to add them all up. Okay. You're trying to add them all up. And once you optimize it, the answer, it's equals to this, and then you take e to that answer, and then you get the result back. So that's the first step. We can turn an optimization problem on products into optimization involving sums by taking logs of everything. Okay, so that's a classic trick that you probably should be familiar with. But there's still a problem because we're trying to maximize these things, whereas most of the algorithms we know about, let's say, shortest path, which is trying to optimize the sum of edge weights in a path, it's to get minimum, not maximum. But now you have to look and think about what's happening. So log, the graph of log, so this is x, and this is y equals to log x. It grows, of course, but at x is equal to 1, log of y, so log of 1 is 0. And when x is less than 1, it's negative and go to infinity. Go to negative infinity. So this is the region that we're interested in because x is between 0 and 1. The f value that they give you is between 0 and 1. So the numbers the log value is actually negative. Okay. If it's negative, well, first of all, many shortest path algorithms like Dijkstra's algorithm, if you've learned that in 3620, does not work with negative weights. But we're trying to maximize. We're trying to maximize this. So if you're maximizing A plus B plus C, let's say, let's just call it, okay, I guess I should put log, but let's just call it L. You're trying to maximize certain things. That's the same thing as minimizing the negative of this. Or, in other words, so if you negate all of these. Instead of taking just a log, we take minus log. Now, all of a sudden, all of these values are between bigger than or equal to 0, so you don't have to worry about negative edge weights. Right, we're flipping this graph, so it's more like this now. So this is the part, and without trying to minimize, we're trying to minimize the sum of these edge weights, and so that's basically a shortest path problem. So here we're transforming a problem that it feels like you're trying to optimize the cost of some path, where the cost is a product, and we kind of trick our algorithm by doing it as a sum, optimizing sum by taking the log. And then we realize that, yes, we're trying to maximize the sum, but those sums are negative. So if you negate it, then it's the same thing as minimizing the sum. And if you got that far, right, then really it's just a matter of using your favorite shortest path algorithm. So if you don't know, in my code library, there is something called Dijkstra-Sparse. Code library. Source. Dijkstra-Sparse. And there's a graph data structure. Here it is. You can initialize the number of nodes at the beginning. And then you call add edge, which says you have an edge from U to V. So this is a single direction edge. So if you have a bidirectional edge, you have to edge it twice. Or you can change this to add it twice. And the way it is right now, weight is an integer, but you can change, right? You can change so you have to be careful and make sure to change all the weights, references to weights to be doubles or any other numeric type. And then you would basically create a graph like this, call add edge multiple times to build your graph, and they're called Dijkstra. Dijkstra will have a graph, the starting vertex, and then a couple of vectors. D is basically the distances to all the different vectors, all the different destinations, and P is a special array that you use if you actually want to construct the path, not just the distances, but you actually get the path. And if you know how to use this code, then it's just a matter of doing it. So this is my code. So I just grabbed it and then I change, the integer weights to double weights. So I have to be careful to make sure I change all the weights to double. And then here in the Dijkstra code, there's one place that I need to change it to double as well. Otherwise, I read n and m. So the problem says you have a bunch of cases when n and m are 0, you quit. So that's there. You build a graph of n nodes. For each of the m edges, I read in the x where the 2 nodes are and the vector. And then I add the edge with weights minus log of f. Then I call Dijkstra starting at 0. And then distance to n minus 1. That's the distance that's the best weight of the best path to the destination. But remember that I take the minus log, so to reverse it, I have to negate it. That negates the negative sign, and then the exponential part negates the log. Okay. And that's how I did that one. Okay. Last one is this flowery path business. So basically, again, you have some starting location 0. You have some ending location 9. That's the highest peak. And you want to figure out basically, I mean, there are a little bit other things you have to do, but you have to figure out not just the shortest path, but any shortest path, because there could be multiple shortest paths. So for example, this path from to the left, from 1 to 4, there are 2 different 90s that you can take. And you can take either way and it's the same cost. Or you can take the other way and it's going to be the same shortest path. So you want to identify all the edges that can be part of some shortest path. And then you add them all up, basically. Add them all up and multiply by 2. But that's not the main issue. The main issue is, how do I know which edge is part of some shortest path? So it turns out to be not too difficult, but the first time that you see it might be a little bit hard to understand. So you have to start and you have your destination, and you can build your graph. So of course you build the graph, and you can run Dijkstra from start to destination, and it will tell you that the shortest path is a certain distance. Okay. Now, it's true that that code will give you a shortest path, but you cannot rely on it because there could be multiple shortest path. Okay. So we have to do something rather than just using the edges that are returned by Dijkstra. Now, how do I know if a certain edge, so a certain edge from U to V in here, how do I know if this is part of the shortest path? Well, if the distance from start and U plus the weight of UV plus the distance from V, hang on, to dest, it's equals the distance from start to destination, then this edge could be part of the shortest path. Okay, because there's a way to get there quickly. And then there's a way to get to U. Then you take the edge from U to V, and then there's a way from you to go to V to destination. And it's the same cost as the shortest path. And so that edge can be part of a shortest path. So what we're going to do is, for each edge U and V, we check. Now that we know the distance, shortest distance between start and destination, whatever that is, because we computed, we use Dijkstra to compute the shortest distance of start to destination. For each edge, we check this statement. And if this expression is exactly the same as the distance, that from start to destination, that's the edge. That's one of the edges that can be in the shortest path. So how do we check this? Right? So remember, when you do Dijkstra, when you call G on start and then D and P, you don't just get the distance from start to the destination, you get the distance from start to anywhere. So this, it's already in your Dijkstra call the first time. So you don't have to compute it again. But this one, you don't have, because you don't have the distances from any V to the destination. But this part, The only thing that changes is the first one. You always end up at the destination. Because these edges are bidirectional, you could actually run Dijkstra from the destination backwards. That's called the reverse. And then this would be the reverse of V. You can do Dijkstra's from the destination going backwards. And then the distances that can get to every other place is the same thing as the distance from that place to the destination. So what you have to do is basically at the beginning, cut Dijkstra's twice. One from the beginning, one from the start, and one from the destination. And then you can look that up for every edge. Now, there is some minor, well, I don't know if it's minor, but there is a detail that I haven't said much about. And the thing is, what if there's some node that is unreachable from either the destination or the start? Because that's potentially possible. In that case, the Dijkstra's algorithm, as is written, it sets everything to distance to be -1. So you need to check before you blindly use that, look up the pref v and all that stuff. If it's -1, you know that there's no path, so you need to ignore that. Okay, so in this problem, maybe I don't remember if it says that every node is reachable. No, it doesn't say that, so you probably should check that if something is not reachable, you should not use it. So here's my code. So again, I just copy and pasted the Dijkstra's algorithm. So I create a graph of the certain number of nodes. I add the edges, and here I only add P1 and P2 in that direction, but where is it? Here in add edge, I change it so that add edge actually add it in both directions. Okay, so it doesn't really matter whichever way you do it, but make sure that you add the edge in both directions. And I run it from the start. I call distance is D1. I run it from backwards from the destinations. I call it D2. And then the total distance from start to finish is D1 to the destination. The sum is what I have to keep track of, but basically what I do is I go through the list of all the edges. So this is my adjacency matrix, adjacency list. So for each vertex and then for each edge in the adjacency list for that, if either one of those distances are negative, that means that I can't reach. If D1I is negative, that means I cannot reach I from the start. And here, if D2E.2 is negative, it means that I cannot go from that to the destination. And then here, this is just the expression check that I talked about. This is a distance to that node, then the edge from the other side of the edge to the destination, and then the weight of the edge. Okay, I wrote U and V, I think, but it's not exactly U and V because my structure has just one single thing, which is a 2. And then where is it from? Where is it from is part of the adjacency list index. Okay, so if you have never seen the shortest path algorithm because you haven't taken 3620 yet, you will see it, but I'm not going to go through this algorithm. But I want you to be aware that there is an algorithm to compute the shortest path from a certain node to all the other nodes, shorter distances, and then one, it's relatively fast. I guess do I have to comment here? Yeah. if you have n nodes and m edges, the version that I have, it's basically n plus m times log of n plus m, which is pretty fast, more or less as fast as we can do reasonably anyway. And then what else do I want to say? Oh yeah, make sure that the edge weights no edge weights can be negative. If you have negative edge weights, Dijkstra algorithm will not work. This is one of the things you'll probably learn in 3620. There are other algorithms that will work, but they are slower. So I want you to kind of introduce you to these shortest path problems, but maybe not the most straightforward textbook problem. Here's the shortest path problem, use it, but something with a little bit of a twist. And hopefully you got something out of it. And I guess next week, the request is to do some kind of dynamic programming problems. So we will choose some for next week. Okay. I'll stop the sharing. Okay, thank you for listening. I'll see you guys again next week.